Hey, 8th grade, welcome back to the garage. A couple days ago, we were wrestling with how in the world I could take liquids that were made of water, salt, a little bit of food coloring, and how they were able to stack up in different layers. You saw in the video that I made that some of the samples would not float, they would not sit on top of a solution of a different color. And so that's odd given that they're all made of the same things: water, food coloring, and salt. Maybe in your mind, as you saw me doing that, you were immediately thinking of the idea, well, I know about sinking and I know about floating, so one of those samples must be heavier than the other. And so that brings us back to the age-old question of which is heavier, a pound of feathers or a pound of gold? And immediately you know that it's a trick question because the weight of each sample would be the same. What would be different is the volume or the amount of space that takes up. So let's reverse the question a little bit. And what if we keep the volume the same? And now that begs the question of which has more mass? A cup of blue foam cubes or a cup of dried red beans? I just use a standard kitchen measuring cup to be able to answer that question. And I'm going to put this one on the electronic balance. And a single cup of blue foam cubes has a mass of about 217.4 grams. So something to consider, 217.4. If I put the cup of beans on the electronic balance now, the beans has a mass of 401.6. So it's a considerable difference in mass, even though both of our samples they are taking up approximately the same amount of space. Another good thing to consider is that you guys remember Mr. Cerny. Before he got into education, his background was in geology. He had a sample of a material in his office that was approximately the size of one of the square Kleenex boxes, not the rectangular ones, but one of the square ones. It was maybe a little bit bigger than that. It was such that I could pick it up with one hand. I could get my hand around it and pick it up. But that cube of material, it weighed approximately 23 pounds. So if you can imagine a 23-pound box of Kleenex, that's what's going on there. So it would be an extreme difference. I don't have that sample to share with you. It was pretty neat to see. But clearly, there's something about the beans that causes them to have more mass than the foam cubes, even though they're taking up the same amount of space. And so that's something to consider, and it's pretty interesting. So if you've reviewed the notes, you know that we're really talking about density. And so the focus question that you've seen on there is simply what is the relationship between layering fluids and now the density of them. And so we were successful in layering our salt straw solution. I just tore it down this morning, so I don't have it anymore. But I want you to make a prediction about the density of these materials that we're working with here. And so I'm going to measure for you, I'm going to try to demonstrate on the balance the masses of our samples so that you can get an idea for what we have going on. So I'm going to start with the red solution. Turn the balance back on again. I found these really cute beakers at school late last week. I have a 25 milliliter one, which works out fine because I have a 25 milliliter sample of red solution. And so the density, or not the density, but the mass of the red solution happens to be 24.4. So if you want to record that somewhere, maybe on a piece of scratch paper, you're going to want to keep track, 24.4. I have a notepad behind me. I'm going to write that down here, 24.4 grams, just so that we're all on the same page. Okay. Let's see, is that zeroed? Pretty close, pretty close. Zero that out again. If I take the orange now, I have another 25 milliliter sample of solution, I'll take the orange. The orange solution weighs significantly more. It looks like it has a mass of 28.4. I'm going to write that down, 28.4 grams. 28.4 grams. I can remove that from the balance. This one's going to have a lot more mass. There we go. Zero it out. I have 25 milliliters of the green salt solution. Oh, all right. You can see that has a mass of 25.9. So let's write that down. 25.9 grams. And finally, if you'll give me a moment, I need to take up a little bit of the blue solution. Only had 3 syringes at the house. Okay. I've got my blue solution loaded. And we'll put the blue solution in, and whoa, look at that go. You find that the blue solution has a mass of just short of 30, 29.9 grams. So actually, I'll tell you what, if you want to go ahead and find the notebook sheet 10, calculating layers of density, there is a table in the top of that you can go ahead and record the mass and volume in your data table here. So just let me read these off again for you. The mass of the red solution was 24.4. The mass of the green solution was 25.9. The mass of the orange or the yellow solution was 28.4. And you can see here still that the mass of the blue solution is 29.9. So you can see back on the calculating layers of density handout, it happens to be notebook number 10. I've asked you to record the mass in the appropriate columns on that data table. What's nice about this example is that the volume of all 4 of your samples is 25 milliliters. And so now let's take a moment and figure out how we can set it up to combine and be able to compare these different values, and we'll relate it into terms of density. If you'll review my notes, you'll notice that density is a measure of how much mass is in some given volume of a material. And so when you have materials of different masses and different volumes, being able to have those 2 pieces of information lets you compare relative densities of things so that we can determine if something will sink or something will float. And you might need density for other applications too. And so, of course, as always, when we want to set up our work, we know that density equals some unit of mass divided by some unit of volume. And so in this case, if I start with the red up here, so I know that my red solution had a mass of 24.4 grams. The volume was 25 milliliters. And that'll give me some decimal number that's quite close to 1. I don't have a calculator with me, but just based on what I know about how fractions work, that'll get me relatively close to the value of 1, which is interesting. You might want to do some poking around on the densities of different materials, and if you'll take a look at the density of water, this value might give you cause for a little bit of pause here. But let's move down to our blue sample here. And so we can set up how we want to solve for the density of the blue sample. And so again, I know that density equals mass over volume. We have a mass value of 29.9 grams divided again by 25 milliliters. And again, based on what I know about fractions, I know that setting up this type of ratio will give me a value that is a little bit bigger than 1. So I don't have a calculator handy, but we would have a value of 1 point something something something, and so we can figure out the relative densities of these things. So now I've left you really to calculate all 4 densities for these colored solutions, but I feel like I scaffolded it pretty well for you so that you'll be successful with the orange and the green solutions. And then take a look at the bottom of the page too. There's a little bit of a ditty there about Bianca and Joel making a salt solution, wanting to figure out where they could get a purple layer to form if they use the solutions above. So think about what's going on there. In this, you are told the volume of the solution, you are told the mass of the solution. Do you have enough information to find the density of it, and where would it layer in our stack of colors? Moving through the rest of the day, take a look at response sheet number 4. Rico is making essentially a snow globe for his sister. He wants to put stars, wants to put some leaves in it so that they settle out at different rates. He's got a salt solution of some known mass and some known volume that he was able to measure. Your first step in that is to calculate the density of that salt solution that Rico's using, and then being able to have those 3 values, you're provided the density of the stars, the density of the leaves. Will his toy work the way that he wants it to? Why or why not? Can you show your math for solving for the density of Rico's salt solution in order to figure that out? And then finally, I am also providing to you a document that will allow you to practice briefly with some of these density concepts. I'm not going to necessarily collect that for accuracy, but if I notice that there are a tremendous amount of errors, then we'll certainly spend more time practicing these math skills. The bottom part of it is pretty interesting. You're comparing salt water and regular water and seawater, and so the question becomes, will a given material, based on the density that you calculated on the top half of it, will those materials sink or will they float in fresh water and in salt water? It's strange to think about. The water that's in the Cherry Creek Reservoir is not the same density as the water that's in the ocean. That's not the same density as the water that's in the Dead Sea. It's not the same density as the water that's in Mono Lake. All those bodies of water have different densities because they contain different amounts of dissolved solutes. They're quite salty, some of them, and so it's going to affect the mass of a given sample of water. And so if you've had a chance to go to any of these locations and play around in them, maybe you experience that. Man, I float really well in the Dead Sea. Don't know, I've never been there. I think it'd be pretty interesting. But take a look at some of these density things. Tomorrow, Friday, when we come back, we'll be looking at, again, playing with a little bit more water, seeing if we can get layers to stack up. Should be pretty good. See you then.